Okay, good morning. So far in this course, we have looked at lots of single neuron models, right? From very detailed biophysical models, Hodgkin-Huxley, and simplified neuron models, which have only two variables, and spiking neuron models. A couple of them we have seen that. In the last couple of classes, we have been discussing oscillator. They're not neuron models; they're strictly speaking models of neural ensembles. So we have seen lots of basically models of single units, right? So now we'll slowly go towards models of networks. So like I've been saying, if you want to construct networks, you have to start with a simple single unit model. Single unit model is too complicated. It's very cumbersome to construct large networks. So we'll start with the simplest neuron model that we have seen so far, right? Which is the McCullough and Pitts neuron model, which is a static neuron model. There's no differential equations there. And with that, we will construct networks, right? So that is the McCullough and Pitts neuron. The first kind of network we will construct is called a perceptron. This is a point where we make contact with artificial neural networks because now we have made the neuron model sufficiently artificial and simple that you can start looking at networks which are also quite artificial, whatever that means, right? So this model was proposed in 43 by McCullough and Pitts. McCullough was a I think physiologist and Pitts was a mathematician. That they wanted to understand how brain works and how brain performs logical operations. So they wanted to basically they were imagining that brain is some kind of a computer, because that was the time when computing was just becoming popular in the background of Second World War. So they proposed a neuron model which is named after them. So this is in this model there is a sigmoidal nonlinearity or a hard limiting nonlinearity. And this neuron takes inputs from several other neurons. As you can see here, the other inputs are x1, x2, and xn. These inputs are weighted by weights labeled w1, w2, and wn. All this weighted input is given to the neuron, this summation, sigma wixi. And if the summation is over some threshold or bias b, right, y becomes 1, otherwise y becomes 0. So we have seen this model before. So therefore g has to be a step function, which is shown here, right? Or people also sometimes we also consider smoother versions of the step function, which looks like this. This is called the logistic function. So this is a step function. So these guys were imagining that brain works like a big computer and neurons are like logic gates, because people knew about Boolean logic and all that at the time very well, and they constructed computers which work on Boolean logic. So their idea is that neurons work like logic gates, like AND gate, OR gate, and all that. So how do you show that? So if single neuron behaves like this, right, where it takes linear sum of inputs from other neurons and passes it through a step function, then that kind of neuron you can very easily show that can emulate logic gates. So look at this expression, for example. Let us say I have a neuron shown here, which has two inputs, x1 and x2. There's a bias term b and two weights w1, w2. By choice of the neuron parameters, that is the weights and the bias, can you make this neuron behave like a logic gate? So, for example, if you take the OR gate, the truth table for OR gate is this: 0, 0, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 1. That means even if one of the inputs is 1, the output is 1. Right? So that's very easy to show, because if you take W1 equal to 1, W2 equal to 1, and bias to be something between 0 and 1. So let us say 0.5. And if G is step function, you can see that even if one of them is 1, x1, x2, the argument is positive. If both are 0, argument is negative. Right? So therefore, you can trivially show that output matches the desired output. Similarly, if you want to get an AND gate, the truth table is here 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 1. That is only when both the bits are ones, the output is 1. That means the threshold should be high enough that the argument is positive only when both the bits are ones. And that is, for that to happen, you need to make the threshold greater than 1 and less than 2. right? So you do that and you get y equal to 1 when only when both bits are 1. Next, we are left with NOT gate. NOT gate is quite trivial because so if the argument is minus x, that is there's only one w, right? And that w is a minus 1, and threshold is plus 5. Then if x is 0, argument is positive, so y is 1. If x is 1, argument is negative, so y is 0. So you can make neurons simply by proper choice of the weight. You can make neurons behave like the three fundamental logic gates. So you can implement any complicated Boolean logic, Boolean circuit using a bunch of neurons. So therefore, they imagined that brain is like a big computer. It's quite natural because that was the time when the world is just seeing the power of computers. So in 1945, that was the time when this ENIAC computer was built, and they were using it for war purposes, to crack secret codes during the war. But this was a huge, clunky computer, and it was filling a huge hall. But since that was very compelling, right? People thought that brain also is like a big computer. This is like a small computer. Sorry. So, but thing is that analogy is quite compelling. It's tempting to imagine like that. But there are many other things about brain and computer which show that two are very different. I mean, it cannot be totally like a computer. Brain cannot be totally like a computer. There are some fundamental differences. Let us see what they are. So, computer is rigid, inorganic 2D sheets of matter. Brain is soft, organic 3D tissue. But here again, okay, we can say that, but actually, strictly speaking, people are now developing floppy chips, this electronic chips, right? Normally they're rigid and hard, but in order to create proper brain implants, in order to implant a chip in the brain, I know one research center in EPFL in Geneva, where they're building chips which are manufacturing chips which are embedded in a floppy biocompatible material, like it looks like a piece of rubber. So in that sense, the chip design is tending closer towards how things are in the brain. Also, brain looks like a big volume, like a 3D mass of tissue. Neurons are very often organized as 2D sheets. Something very interesting about that. It's a fact. Very often, not always, but very often, the organization of neurons is in the form of sheets. If you look at the cortex, which is surface of the brain, is covered by a sheet of neurons, about 2 to 5 millimeters thick, and that's also a sheet. Like it has multiple layers, but it's a sheet. And now, powered by DC mains, powered by ATP, actually instead of DC mains, brain has four major arteries, right, entering it from in four different points, and these arteries carry oxygenated blood to pretty much every point in the brain tissue. There, the glucose and oxygen from the blood is converted into ultimately into ATP or after a series of steps. And this is chemical energy which is used to power the right neural activity. So in that sense, the power distribution methods are quite different between brain and a computer. Also, if you look at the nature of the signal, in a computer, the signal is a digital signal, so things just go up and down. If you just tap any bus, any line in a computer, right, it will look like something like that. Just the voltage going up and down between two hard limits. Whereas in case of a neuron, it doesn't look like that. It has the spikes, right? And another thing is in the computer, although the signal doesn't look regular or anything, doesn't have to look regular. The frequency of the signal, the underlying time period of this, that's fixed, right? That is determined by a kind of universal clock, which drives all the operations in the computer, right? And these clocks are also the very high frequency, right? Order of gigahertz and all that. But in the brain, there is no such centralized clock. So computer has a centralized clock, brain has no centralized clock. And different parts of the brain have their own local frequency, if you can call it that, because a given neuron can have variable frequencies. The frequency of the action potential is varying. That's why we talk about a rate code. The frequency is constant. There's no question of rate code, right? So we can only talk about the limits. And compared to the computer, the brain's frequencies are extremely slow. because the computer goes in nanohertz and all that, and the brain, the highest frequencies are about a couple of hundred hertz. It's a very slow. But computer makes up for that loss by having lots of tiny processors, right? The brain makes up for that loss by having lots of, because in a computer you generally have one big processor. If you look at this multi-core processor, you might have maybe a few dozen. Like there are these parallel computers which have large number of processors. The largest I have seen is one that was uh, produced sometime in the 90s, something called a connection machine, which used to have 64,000 processors. But after that, but the single processor is very small, right? Whereas the modern cores, single core itself is quite GPUs, which is very complicated. But the number of such GPUs is not very high. So in the brain, you have 100 billion neurons. I mean, no computer can come anywhere close to this number in terms of basic processors. But then maybe that comparison is not fair because the single neuron is not like a basic processor in a computer. I mean, single neuron is much simpler. So you can keep arguing back and forth because it's very hard to draw parallels, but it's good to have both these set of facts on the table and observe them simultaneously. But one area where a brain really beats the computer is power dissipation levels, right? 10 power minus 5 watts in a computer uh, per bit, right? Whereas in a brain, it is estimated to be 10 power minus 12 watts, right, per binary operation. So all these are fine, but in fact, a more fundamental difference between computer and the brain is computer is programmed, right? It's pre-programmed. You have to tell it what to do, and it will keep doing it. Follow those rules and keep doing it. Whereas brain learns from experience. Okay, and one more thing that's very different about brain and computer is that brain is extremely fault tolerant. Right here. Right. So there is a, even if there's damage, right, it can take a lot of damage and still continue to work. Right. I mean, like, imagine what happens when when you're frustrated about something, how you messed up some exam, and you kind of bang your head on the wall a little bit, not too much. So you have your nice cerebrospinal fluid which cushions all the impact, and right, no major brain damage occurs because of your frustration. But try doing that to a computer. I mean, you take your computer desktop, very angry about something, you just give it a hard shaking one day, and see what happens, right? Or there was a time when in the early, like in 2000s, early 2000s, we used to buy these slightly cheap computers, because there was a big drive to save money and all. So because of a lot of dust, we didn't have AC at that time. There was a lot of restrictions on use of AC. So there's a lot of dust in the air, and because of dust, the PCBs, the boards in the computer used to have develop loose contacts, and it stopped working. All that you have to do to fix it is, right, open the chassis and clear the dust, and it will start working again. So something as small as dust in the air can make this computer stop working. So it's so delicate. I mean, whereas brain is other extreme. So there's classic case of this guy called Phineas Gage, who was this person was working in the U.S. in railroad industry in the 19th century. So his job is to soften the soil right before you lay the rails. So he would do that by using explosives. So one day he was digging a hole and packing dynamite inside that hole, and it exploded while he was still packing it. So the crowbar with which he was packing it, went through his head and kind of penetrated his prefrontal cortex, and the front part of the brain is all completely damaged, a big hole. So this guy survived that accident. He was operated on, and they removed the crowbar from his head, and he survived. He had a life. He was not normal. I mean, this was serious personality changes, but he lived. So just for comparison, imagine driving a crowbar through your through your desktop, right? That will be enough story for the desktop. So these are some examples to show that brain has a very different kind of a design, that extremely fault tolerant and low power usage. And most importantly, it learns from experience. It's self-learning, whereas computer has to be taught. So this is there's some fundamental differences. So keeping this in view, people drop the analogy between computer and brain and drop the logic gate story of neurons. So in the 60s, this guy called Frank Rosenblatt, that he proposed a new kind of approach to training a neural network. The idea of training was introduced at that time. So instead of setting the weights, right, by some kind of a calculation, right, he said we can train the weights by exposing the neuron to some patterns and let it learn those patterns. So he showed how you can take the same Macaulay and Pitts neurons and train them to classify patterns. Now, how do you do that? So that led, gave rise to this network called what we call a perceptron, because it's a machine that perceives, and they would, because of they would call machines like electrons and protons. They gave some kind of a name like that, so that became a perceptron. So in this network, there's a bunch of Macaulay and Pitts neurons which receive an input. Input could be an image if you are trying to classify visual patterns. Then, depending upon the output of this layer of neurons, you can find out what the input pattern is. Let's take the simple case of a single neuron, and let us say I want to classify an input image into just one of two classes. Is it this or that? Right? Because the n class problem is a trivial extension of that. So I give an input to this single neuron. If the output is 1, it is class 1. Output is 0, it is class 2. So that's how I want to do it. Then the question is, how do you train these weights and the bias for that to happen? So there's a bias term here. How do you do that? So the classic way to do that, which we will use several times in this course, is imagine your neuron is inside this black box, which is labeled neural network. I give an input to this network, input X. I get some output Y. Right, I want the output. So if let's say X is in class 1, I want the output to be 1. X is in class 2, I want the output to be 0. This is what I desire. Now output could be 1 bit, output could be a vector, doesn't matter. Now I compare the actual output of the network with the target output or desired output, right, T. And look at the difference, T minus Y, and this error is then propagated to the network, right? And then I change all the weights in the network in such a way that next time around I give the same input, the output Y will move slightly closer to the desired. So you keep doing it over and over again, right? And the output will slowly tend towards the desired. The actual output will tend towards the desired output. So this is kind of like how you teach a small child how to, let's say, read, right? So imagine you are teaching your little nephew or niece how to read alphabets. So you show the letter A and they ask the child to say A. The child says A, you say that's very good, and give a lollipop or something, right? If the child sees A and says B, right, you get upset and you yell at her or whatever. So like that, you give the correct response, and you gently nudge the system to adjust its response so that its actual response is close to the desired response. So for that, we need to have something called a training data set. So you have a bunch of inputs like X, right, and a bunch of desired outputs D, right, and a bunch of actual outputs. Our goal is to make sure that the actual output Y is close to the desired output. So this is ideal. And in this case, I'm looking at a single neuron. I'll come to multi-neuron case later. All right, Y is equal to G of sigma Wi xi minus B. So for a given vector X, right, and the output should be equal to the actual output should be equal to Z output. So how do we do that? Like I said here, I want to minimize the difference between the actual output and the desired output. So I can do that by formulating something like an output error, E, which is equal to this summation. So P is the index over patterns. That means, in this table I have lots of patterns, right? So I just take a summation over the patterns of d minus y whole square with a half in the front. The goal of training is now how to find w's and b in such a way that they minimize, right, the error e. How do you do that? One way to do it is just take the derivative of the error, right, del e equal to 0 with respect to b and w, and solve it analytically. But that is not possible in general if you have a very complicated network. So what we actually do is go for an iterative solution. So the way we do it is I have an error function e, right, and I start from some point. I make an initial guess. Let's say that is this point. Now let us say I have only one variable, one weight value. Okay, and this is my error profile. I want to go to this point because that's where the error is. Ideally, error should be 0, but even if I can't achieve it, I'll go for a minimum error. So I need to go to this point. I'm right now here, right? If that means error is now this value. So how do I know that I have to go to left? Because if I take the derivative of this error with respect to weight, right, that is negative here, right? So, and then you know that you have to move in the positive towards the left. It's reduce. Sorry, the derivative is positive, whereas the weight has to be reduced here. So, right, similarly, if you take a point on the other side of this minimum, so you can see that the derivative is negative here, and you can see that I have to increase the weight to go towards the correct solution. So you see that all that I have to do is move in the opposite direction of the derivative, all right, to get to the correct solution. So in the multiple dimensions, the same thing works out like this. So I change the weight wi or delta wi in such a way that I move in a way proportional to the derivative of e with respect to wi. Right. So similarly, if I take the vector delta w is proportional to minus del of w of e, del of e with respect to w. Similarly, for bias also, delta b is proportional to minus dou e by dou b. So this is called gradient descent, and we'll derive an expression for perceptron using this approach later. Now, what does a perceptron do? It's like I said, if you take a single neuron, it classifies the input into two classes. And how does it do that? Let us see this. So as you can see that if the argument here is positive, y is 1, otherwise y is 0. So the borderline between so that means for every point in the plane, in the x1 and x2 plane, y can be 1 or 0. So for some points y is 1, some other points y is 0. So if you ask what is the border between the y equal to 1 region and the y equal to 2 region, that has to be the place where the argument is 0, right? So if argument is 0, that becomes a straight line. This is a straight line. So this straight line separates all the points where y equal to 1 and points where y equal to 0. So therefore, this neuron is basically dividing the input plane into two semi-infinite halves, right? Where in one half y equal to 1, other half y equal to 0. So you can imagine same thing happening even in multiple dimensions, when the input is an n-dimensional vector. So where if x is in Rn, the neuron divides the entire input space into two semi-infinite halves. So let us see a numerical example of how a neuron can be used to train to learn let's say the OR gate. So this is the truth table of the OR gate. We've already seen that. So that it has 4 points, right? This is the 0 case. These 3 are 1 case. So basically, I need a separating line, which is something like this. So then the points on this side will have one class. Points on this side of the line will have another class. But I randomly initialize the weights and bias like this: 0.2, 0.3, and minus 0.2. For these values, my separating line is this blue line. So which is wrong. So it's putting all 4 points in the same class. So it is wrong. So if I present the pattern 0, 0 as input, right, instead of giving 0 as output, it will give 1 as output, because the 0 is also on the same side of the line as other points. So I give then 0, 1 as input, and it gives correct classification because on the positive side. 1, 0 also gets correct classification. This one, 1, 1 also gets correct classification. So for this separating line, out of the 4 patterns, 3 give correct answers and this one gives wrong answer. So I have 75% accuracy, right, for these weight values. So then I apply the learning rule. I didn't say what it is, but I'll give it in a minute. Apply the learning rule and change the weights. With these new weights, now the weights have jumped to these new values, 0.2, 0.3, and minus, okay, 0. For these values, now the weight, the separating line has jumped to this level. And you see that from this point on, right, the 0, 0 point is on one side and the other 3 points on the other side. So it's a very nice, it's a proper separation. And you can verify that easily. So if I give 0, 0 as input, it'll give 0 as output, so which is correct. For 0, 1, it gives 1 as output. 1, 0, it gives 1 as output. And 1, 1 also gives 1 as output. So all the 4 are correctly classified because it got this as a correct classification. So so you see that now I need to, so I have 4 points like this, right? Basically my neuron or perceptron should find a separating line which can separate these 3 points on one side and this 1 point on the other side. So I can do that by drawing many possible straight lines. So you see that any of these lines would have worked, right? So you see that there are infinite number of solutions possible. So the solution is not unique. But the thing is, the solution is, for the solution to be possible, right, the point should be such that you can draw a line and separate the 2 sets of points. So these are class 1 points, these are class 2 points. It should be possible to separate the 2 classes using a straight line in 2 dimensions. And if it's n dimension, it should be possible to separate them using a hyperplane. If that is possible, then you say that the classes are linearly separable, that it's possible to define as hyperplane which separates 2 classes. So basically you are saying that solution exists, right? Because that's the kind of solution the perceptron will discover. So when you say that the sorry, patterns are linearly separable, it means you are just saying a solution. The perceptron has a solution. So this data is linearly separable, whereas if you look at the example on the right side, the blues and the greens cannot separate by drawing a line. There will be a problem no matter what you do. Okay, so this is not linearly separable. So perceptron works only when the data is linearly separable, and when they are linearly separable, normally there will be infinite number of solutions. So there is no unique solution. But take this problem, a different logic gate called the XOR gate. Right, the truth table for this is like this: 0, 0 is 0, 0, 1 is 1, 1, 1 is 0, 1, 0 is 1. So if the number of ones is odd, right, desired output is 1. Number of ones is even, right, desired output is 0. So if you draw this graphically, right, the 2 points, so the class 1 points are like this, the greens, and the class 2 points are the blues, right? So I cannot draw a line to separate the greens and the blues. So there's no solution. The first one will not find a solution. All right, and so that's a limitation. It shows that it will work only for linearly separable patterns. Now there's a small variation of perceptron where the nonlinearity is not step function, but you can use a smooth sigmoid. So what we have seen before, all the arguments we have presented until now involve like a step function, or you can also take a smoother version of this, a logistic function, a smooth sigmoid function. So then again, it will work very similar, right? Again, if you take this argument, so to be equal to 0, then that will give you a straight line as a separator in 2 classes. And the update rule, now let me derive that. So we said the update rule is, or the weights is derived by minimizing the output error, right? So if this is output error, sigma dp minus yp whole square, right? So like I said, we train the weights and bias by using gradient descent. That means negative of del E versus, with respect to W, or del or dou E by dou B, right? So if you do the algebra, right, as it's done here, so delta W is equal to minus eta times del E. So that works out to be so eta times d minus y times g prime, right, times xi. So g is a smooth sigmoid function, the logistic function. So you can take a derivative of that. We could not have done that previously with the step function, because the step function derivative is zero almost everywhere except at the origin, but then derivative is not defined. So there's a problem there mathematically. So you get around that in a different way, but I didn't talk about all that. There's a different way of deriving this learning rule. So delta W is equal to eta times d minus y g prime xi. Similarly, if you work out the math for dou E by dou B, you get delta V is equal to minus eta d minus y g prime. Okay, so you get these two equations. So then we make an assumption. So g prime is always positive, because if I take the logistic function and look at its derivative, it looks like this. So the highest value is so if you take the logistic function expression to be like this, 1 by oops no place 1 by 1 plus e power minus lambda x. So lambda is typically greater than 1. Okay, so the highest value of the derivative is equal to lambda. Now, so and lambda is positive. So you see the g prime is always positive, and as you go away from origin, the g prime value goes down, but it's always positive. Since g prime is always positive and the eta is also a positive constant, right? We'll just observe. We can absorb that into eta and define a new learning rate called eta prime, right? And then the learning equation simply becomes delta wi, right, is equal to some eta prime times d minus y times xi. Similarly, delta b is equal to minus eta prime times d minus y. So I got rid of the g primes by these arguments, and I have such a simplified simplified set of learning equations. So only thing is here the step size eta is now variable, right? But then what we will say is, okay, let us, so you can have a learning rule. Once you have the update rule, you can iterate it with variable step size or a constant step size. It doesn't matter as long as the step size is small enough that it doesn't become unstable. The iteration doesn't become unstable. So I'll apply these arguments and say that eta prime is constant and a small number. So that gives the final update rule, right? Delta wi is eta times d minus y times xi, right? And similarly for delta b, it is minus eta times d minus y. Okay, these are the two update rules. So these are called these are called the Perceptron learning rules. So there is a different way of deriving this learning rule without invoking the gradient descent approach. I haven't done that. It takes a little while to explain that. So anyway, these are the learning rules, and so it's a very nice learning rule, and it has another important property, which is called the locality principle. That is, if I have a neuron here, right, and I'm training this on some input. So input is x1, x2, xi, xn. Right, I'm training a given weight wi. Right, how do I do that? Wi is equal to okay. Let's say I have multiple outputs, right? And output index I'm saying is I, and input index is j. So then the weight between input and output will be wij, which connects the jth input neuron with the ith input neuron. The update rule is still has the same form. You can easily work it out. It is eta times di minus yi times xj. So what does it mean? So if I am a neuron here, my state is xi or xj, and if I have a neuron here, my state is yi. right? The update of this Wij is given by the desired value also available at the output D, right? So update value for the weight is given by D minus Yi and or Di minus Yi, and this information is present in this neuron or at this neuron. It's available at this neuron, and Xj is available at this neuron. So at that, and I just need the product of these two quantities to update myself. So if I'm a weight sitting here, right, and Wij, I get the d minus di minus yi term from here, and I get this xj term from here, right? Both are used to update this weight. So physically, if you think of this as a physical process, it is quite plausible. That all that we are saying here is, okay, there is a synapse here, and there is some activity going on the postsynaptic side, some information from the presynaptic side. The synapse is basically collecting information on the presynaptic side and the postsynaptic side and adjusting itself. This is physically plausible, because it's important to note this, because later on when we derive learning rules for a large network like a deep network or a multilayer perceptron, you'll initially bump into a problem where to update a synapse here I need information which is very far off from the synapse, which is physically impossible. Whereas, so you always want to, any learning rule, to satisfy what is called the locality principle. All the computations occur locally based on local information, right? You don't, for it to compute one variable, you should not be requiring information from very far off places in the network. This is one more nice thing about a perceptron. But the real problem with a perceptron, as we have already seen, is that it can only work with linearly separable patterns, but real world data is much more complicated. Real world class data is much more complicated. So it will fail in such cases. So all these aspects were very nicely brought out by this book by Minsky and Papert on perceptrons. Ironically, in that book, they gave some damaging criticism, right, of the perceptron and how it has lots of good qualities, but it is limited by this linear separability condition. So they said it's no good. So because of that damaging criticism, this book, which came in the 60s, I believe, right, really slowed down. And okay, so what they said in their criticism is that they said it's obvious that the perceptron has all these limitations, which is clear mathematically. But the extrapolation that they did based on that is what was wrong, and it created a lot of problems. They said as a perceptron which doesn't have any hidden layers, because in the perceptron you just have input layer and output layer, right? And there's nothing in between the two. Okay, so you have output layer and input layer. There's nothing in between the two. So there are no intermediate layers. So they said even a two-layer network has such serious limitations. So there is no point studying networks which have more layers. This was their criticism, which is actually totally backward, right? Which is not at all even logical. But that's what they said. I mean, I don't have the exact quote right now, but it's there given in a lot of books. So that discouraged people from studying multi-layer versions of this perceptron for a long time. So this was in the 60s. Okay, perceptron was proposed in the 60s by Rosenblatt, early 60s. And throughout the 70s and 60s and 70s, there was a lull in research. So in the 70s, one guy called Paul Verbose studied multilayer networks and derived learning rules and all that, but that didn't become popular. Nobody bothered about them because people were scared of criticism. But later in the 80s, again, I don't know, maybe Minsky died by the time, I don't know what happened, but people, kind of emboldened themselves to take up research on multi-layer networks again and derived learning rules. And that, led to explosive research. And suddenly, in a close span of a couple of years, several groups studied these networks, these multi-layer networks, derived learning rules, and published them, and did a lot of studies based on such networks. And it really triggered the neural network revolution in the 80s because of all those developments in the 80s. But for a long time, for almost 2 decades, there was the research slowed down. So this multilayer perceptron is different from perceptron, first of all, in this important aspect, which is there are hidden layers, layer or layers. There should be at least one hidden layer. And typically they use a smooth sigmoid and not a hard limiting. They don't use step function kind of thing, but they use logistic function. Or instead of using the signum function, they use a tanh function. So this is a typical architecture of a multilayer perceptron with a single hidden layer. There's an input layer and there's output. Output can have one neuron or n neurons, right? And then there's a hidden layer. Now there is a mathematical theory which says that a network like this can learn kind of any is somewhat vague mathematically. I'll make it more precise later, right? Even if the data is linearly non-separable, it can learn that, but I'll make it more precise later. So you can easily show how a multilayer perceptron can learn something that a perceptron cannot learn. So the big counterexample that people have been using, right, to beat down perceptron is the XOR problem. That you can show very easily that a multilayer perceptron with even a single hidden layer can learn the XOR problem quite trivially. So how do you show that? You don't even need to train the network, simply by kind of a hand calculation. You can show that the MLP can learn the XOR problem. So consider an MLP which has a single hidden layer. So it has two inputs, x1 and x2, and then there's a single hidden layer which has two neurons, and then the single output layer. So the outputs of the hidden neurons, I'll call them V1 and V2. The output of the output neuron, I call it Y. Now there's some bunch of weights here, let's say, and I will now define the input-output relationships of all these neurons like this. So V1 is, right, let's say G times. So I have all these, imagine I have all these weights here. So this is W11, this is W22, and this is W12, and this is W21. So I have all these weights. I'm not showing it because the picture gets cluttered. Now imagine that W11 comes here, right? That is equal to, so W11 is equal to 1, W12 is also equal to 1, right? And bias equal to bias 1. So I'll call this bias 1, B1, right, is equal to 0.5. So this is W21, this is W22, both are equal to 1. And bias B2 is this, which is 1.5. So let's say I have chosen the numbers like this. I'll tell you why I have chosen like this. In output Y, I have one weight here, I'll call it W1, another W2, and bias here, I'll just call it B. So W1 is 1, W2 is minus 1, and B is 0.5. So why did I do this? Let's look at this. So V1 is given by this x1 plus x2 minus 0.5. That's like basically your OR gate. So your separator is something like this. So V2 is the x1 plus x2 minus 1.5. That's like your AND gate. The separator is somewhere here. Now imagine I do V1 minus V2, the function V1. Right, in the function V1, the output is 1 here in this entire region, and output is 0 in this entire region. For function V2, output is 1 here in the entire region and 0 here in this entire region. All right, so if I subtract this from this, I get this strange function, which is where the value output value is 1 inside this strip, the infinitely long strip, right? And on both sides of the strip, my output is 0. This is for the quantity by V1 minus V2. Now in the actual output neuron, which is given the Y equal to this G of V1 minus V2 minus 0.5. So basically I have taken the V1 minus V2 and subtracting 0.5 from that. So then what happens is this strip will have value of 0.5 on both sides. On the flanks, it will take value of minus 0.5, the 0 minus 0.5. So now if I pass this quantity through a step function, what do I get? Because the argument is positive here and negative here, therefore the final output Y will be equal to 1 in this strip and 0 on both sides. That's exactly what you want for XOR gate. So basically we were able to show using a counter example that a MLP can learn something that the perceptron cannot learn, and MLP can learn linearly non-separable classes. But this we have done by some kind of hand calculation. You cannot do it for a more complicated problem. You need to derive a learning rule which will work for any case, right? So we will do that in the next class, right? And then I will show you some examples of how the multilayer perceptron MLP or its more recent cousin, the deep network, both are the same actually. Okay, and deep network can be used to explain lots of interesting phenomena in the brain. So that's all for today.